Hello everyone, and welcome back to our lecture in computational finance. In the last lesson we looked at the use of Monte Carlo simulation for pricing financial derivatives, for pricing options. Now remember that in all of these examples we are looking at here, we don't know the true fair price. Obviously, if this were a real life setting, we would have to look at the market price. And if we are very certain that the market price is right and the market is complete and arbitrage-free, then obviously the physical real price would be the fair price. Now, in all of these settings, we assume that with model assumptions and in this model setup, that the Black-Scholes price is the true, fair, arbitrage-free price. And with Monte Carlo simulation, we are trying to get as close to the Black-Scholes price as possible. This means that in all of these examples, and it's the same here with the down and out or down and input, for most of these examples here, we wouldn't actually need Monte Carlo simulation because we have Black-Scholes at our disposal. Those are still plain vanilla options, and we could have used Black-Scholes instead. But to show how Monte Carlo simulation works, this is just fine, and you can see how actually Monte Carlo simulation gets quite close to the Black-Scholes price, and you only need to increase the number of simulations. Now we wanted to improve on our last model, on our last algorithm for Monte Carlo simulation by incorporating correlations and by incorporating additional information on our underlying and our derivative. And what we are trying to achieve in the end is a variance in the reduction of the estimator, because we are estimating the option price, which is the mean of all our simulated option payoffs, and we want, as you might remember, actually here we always fitted a normal distribution to the mean, to the payoffs of the option contract at t0, and then we calculated the mean, and we also had a confidence interval, and we wanted to decrease the variation of our estimator, that is, to reduce the size of the confidence interval. So this is why in the next step we are looking at conditional Monte Carlo simulation as an example of variance reduction. Okay, so the starting point is the equation PDO, the price of a down and out put, equals the price of a regular put minus the price of a down and in, of a knock-in product, a down and in put. Assuming now we divide the term of the option into intervals of length delta t, so that we have capital T equals m, for example m days, times delta t, then an underlying path. This simulation of the underlying is given by S1, S2, S3, and so on, and Sm. Now we then estimate the option price using, for the down and in put, we take the expected value of the payoffs. Now the payoffs are actually given by the strike minus the final underlying price. It's this difference, if this difference is positive or zero otherwise, times an indicator function, and the indicator function is 1 if for at least one j we have the underlying price at time j is smaller than the barrier SB. Now what does this mean? This indicator function becomes 1 if the put has been knocked in, if the barrier has been crossed once below, or 0 otherwise. So we only have the put payout in case the option has been knocked in. And then we take the expected value, we take the mean of the payoffs, and we discount this using capital T and R as the interest rate, or it's 0 otherwise. That's the option price for a down and input. Now let's use this in MATLAB. The down and output is simply, if we insert all of this, Then the down and output, MC, if we enter all this, gives us this price. Again, we have, let me just check if there is a, actually this slide is twice in here. Okay, have to correct that. So let's getting back to the down and input. Let J star be the time index at which the barrier is crossed for the first time. So we set J star equal to m plus 1 if the barrier is not exceeded during the term, meaning that if J star is m plus 1, it has not been knocked in, but at time J star times delta t, it's knocked in, option is activated, but after that, the option, the down and in option, is nothing but an ordinary vanilla put. So if you're given the crossing time, T star, J star times delta t, and if you have the then current underlying price as J, you can actually use the Black-Scholes formula afterwards, meaning what? Let's assume this is the stock price and the barrier is here. Well, at this point here, if it's a down and input, at this point, you know this is J star. At this point, you know that if you are only looking at this time horizon, then here it's a plain vanilla put. So what we are actually doing is we are simulating paths via Monte Carlo simulation, and we are only using the simulated paths of the underlying to determine J star. And after J star, you only need to calculate the option price of a put for this underlying path, for this simulation, in time J star, and then discount it to T0. And this is, for this we use Black-Scholes. So if the barrier is exceeded before maturity, we have the following results, that actually this needs to be equal to the Black-Scholes price of a regular put in J star, and we then need to discount this using capital T minus T star to actually T0. Okay. Now simulating a path S, we can then use this estimator indicator function. S, is the product knocked in? If yes, then use the Black-Scholes price at time J star and discount it to T0. Otherwise, it has to be 0 because it has never been activated. Now, note that this conditional Monte Carlo simulation differs from the previous procedure in that the conditional Monte Carlo simulation does not discount the simulated payments in capital T, but actually the option prices from the Black-Scholes model in T star. Now, one could also say this is a little bit sneaky. Why? Because actually we're using Monte Carlo simulation, but only to determine the point in time when the option is activated, and after that it's still regular Black-Scholes model. Again, let's assume this is, where's my cursor here? Okay, let's assume this is the Black-Scholes price. We would probably assume that if we use Monte Carlo simulation, the confidence interval will look like this, and if we in part substitute Monte Carlo simulation by incorporating Black-Scholes, probably the interval will become smaller. Let's see how this works in MATLAB. So it's the down and output MC cont for conditional Monte Carlo simulation. We generate the asset paths and the payoffs for the down and in option. The payoff zeros, time zeros, stochastic value zeros. And then we simulate path again with our asset paths function, that's geometric Brownian motion. T crossed is the minimum of find the point at which path becomes smaller or equal than SB, that's the barrier. And if T crossed, if it's not empty, then N crossed equals N crossed plus 1, count it up once, times N crossed equals and so on, and nothing happens. If N crossed is larger than 0, then use the Black-Scholes price, and then again you need to discount this, the Black-Scholes price, and then we have the payoffs, we have the price, the prices actually of the down and input, and we're actually interested in a down and output. So remember that actually the down and input is a put minus the payoff. So put P minus down and in. That gives us the down and output. So actually we are using the equation for the down and output and using this results for the down and input to price the down and output. Okay, now if we do this, the down and output gives us a price of 3.8645 and we get a price for the down and output with Monte Carlo simulation, 8751, close enough. And you can see we have this 85, 89 confidence interval. And if we now do the conditional Monte Carlo simulation, it's 8617 and 8684. So yes, the confidence interval becomes much smaller for the conditional Monte Carlo simulation. Okay. Again, now for most of these options, for these plain vanilla options, you don't need Monte Carlo simulation. You can simply use the analytical formula from Lex-Goltz. Now let's use Monte Carlo simulation for an Asian option, and we are looking at an Asian average rate call option with discrete arithmetic averaging. So this is an exotic option, and the payoff function is the maximum of 1 over n times the sum of all those stock prices minus the strike. So you take the average stock price, you subtract the strike, and the maximum of this or 0 is paid out. Now we assume that the prices are measured at equidistant times, so it's, for example, the closing price, the closing quote every day. And then let's price this option again using simple Monte Carlo simulation. Very, very simple. Again, we start by defining this function and calling it Asian MC. The input parameters are the current stock price, strike, interest rate, maturity, volatility, n samples, n REPL, and the number of replications. And then we initialize payoff using zeros. We simulate n REPL asset paths as before, and the payoff in simulation I in line 6 is, well, very simply, the maximum of 0, mean of path from 2 until the end minus the strike, and then it's just the regular Monte Carlo simulation we've done so far. We fit a normal distribution to the discounted payoff, and we get the price and a confidence interval. Now, as you can see, this is an Asian option, Asian arithmetic call and average call, and Monte Carlo simulation takes us 8 lines in MATLAB. You need to have a function in place for simulating from a geometric Brownian motion, and then it's only a matter of simulating the asset paths and then taking the average and discount this, and then you're done. Now, we want to improve this simple approach by adding control variables. And the general procedure for reducing, again, that's the ultimate goal, reducing the size of the confidence interval, reducing the variance of the estimator. And we want to do this using control variables. And the general procedure is the following. Let's assume that we intend the estimation of theta being the mean of x. Now, if we have another variable, y, that is correlated with x and has the expected value nu, we call the variable y a control variable. And we can then use the so-called controlled estimator, xc equals x plus c, function or parameter c, times y minus nu. Okay. Now, why should we use xc instead of an estimator for x? Well, actually, the mean, the expected value of xc is theta. So yes, if we want to estimate theta, then we can also use xc and estimate xc. Same expected value. But the variance of xc is the variance of x plus c squared times the variance of y plus 2 times c times the covariance x and y. And c is now estimated by taking the negative of the covariance divided by the variance. And now we arrive at an unbiased estimator. It's clear from the fact that the expected value of xc is theta. and the estimator has a lower variance, a smaller variance than the original estimator for x. Why? If you take the variance of xc star, using c star, divided by the variance of x, it's actually given by 1 minus the squared correlation between x and y. So if you have a correlation that is non-negative, that is non-zero, you will have a smaller variance for the controlled estimator than for xc. I hope this is clear. So it's unbiased because it's theta that we get as the expected value of xc, and actually the variance of xc is smaller than the variance of x in case we have a non-zero correlation. Now, one option for the control variable could be the sum of the underlying prices. We need a variable y that is correlated with x, positively or negatively. Now, this option has the advantage that we can determine the expected value e of y. Y is obviously correlated with the option price, in this case of an Asian average call. Another choice could be the price of an average geometric option, whose price is analytically known. We don't have this for the arithmetic option. Could be. Yeah? And the expected value of the sum of the underlying prices is y. So, under the risk-neutral measure, we get the expected value of y is the expected value of the average underlying price, expected value of sum of the expected value of each of these stock prices, and now we use the geometric Brownian motion, we insert this, and we arrive at this here. You don't need to memorize this, only accept this, that under our model assumption, this is what we get, the starting underlying price and this. So let's value the Asian option using the controlled estimator. We call this function the Asian MCCV. We need two set of replications, two set of simulations. We first simulate asset pairs to estimate the average stock price. And then we do a second set of replications, a second set of simulations to price the options. So we do this the first time, tri-path, asset path, and so on. And we say the stock sum is the sum of tri-path. So this is our control variable. Now PP is the mean of the tri-path, and we then calculate the payoff, and we estimate the correlation. So this is the covariance of stock sum and tri-payoff, and then C, the parameter, because again, remember, we need the covariance between x and y divided by the variance. So we take C as minus the MATLAB, that's the matrix that has the covariances, divided by the variance of stock sum, and then it's the same as before. We have to initialize dt and simulate another set of asset paths that we can use in the pricing of the option. And as you can see here now, control vars, that's the payoff x plus c times y minus mu here, the expected sum, which is the expected value of our control variable. And then we fit a normal distribution to control vars, which holds the values of xc, the payouts, the option payouts of the controlled estimator. And if we now do this and compare it with Monte Carlo simulation, we don't have black scones at our disposal here, so we have to compare regular Monte Carlo simulation with Monte Carlo simulation that uses a control variable. Yeah? So again, Asian MC gives us a price of 3.9939, confidence interval 94 to 04, and we now get a confidence interval with a control variable of 93 to 97. So yes, actually here you can see the confidence interval becomes smaller. Not too much, but it becomes smaller, and you can obviously also use additional control variables. And the higher the correlation, between x and y, the higher the reduction in the variance will be. Okay, so this was Monte Carlo simulations. Again, a very simple approach. You need to have a model for simulating asset paths from the underlying, or the model for the underlying, and then you need to insert it into the payout profile. And in regular Monte Carlo simulation, you only need to insert them in the payout profile, discount it, and take the average. If you want to do it in a more sophisticated way, you need to use control variables, or you need to incorporate additional information on the option contract you might have. Okay, so next we'll have a look at finite differences. Now, we already know that the value of an option at time t on an underlying with price s is a function in the stock price and in time that satisfies this following well-known stochastic partial differential equation. This is, again, if you don't remember it yet, this is the Black-Scholes differential equation. And we need suitable down boundary conditions to solve this stochastic PDE. Now, a very, very simple idea to solve this. Think about this for a minute, and then I'll give you the solution. Have a look at this equation. It's a stochastic partial differential equation. And the thing that makes this quite difficult is the fact that this equation includes, well, derivatives, Ableitung. Derivatives of the function, partial derivatives of our function f. And think about this for a minute. What could you do to solve this as an approximation? We are sure we cannot do this exactly analytically, because then we would again need to arrive at a solution like Black-Scholes. But what could you do to get an approximate solution to this equation? Remember, we have derivatives here. Well, think about this the following way. Remember what you would have done in school. If, for example, this is the function, and remember that different, and you want to know the value of a derivative, blue color here, let's say at this point. Now, what is the value of the derivative in this point? Well, the value of the derivative, as you might remember from school, is, is the slope of a linear function of the tangent in this point to the function. So that's actually the slope of this blue line is the value of the first derivative to this function in this point. Now, how could you approximate? How could you get an approximate solution to this slope? Well, if you don't know how to calculate this, you can simply do the following. For example, I'd remember that the slope in this case would of course be, also, you could simply use a triangle. Well, that's to calculate the slope in this case exactly. It's this slope. Well, the ratio, that's the English word, sorry, the ratio of the length of these two sides. Now that's the slope. Okay, now what could you do if you don't have the blue line? Well, let me just delete this for a second. If we want to approximate this, well, you could simply do the following. You can take this point, and you can take this point. You take these two function values, and you combine these 2 points. Then, obviously, you would have a very coarse approximation to the line, to the first derivative in the point in the middle. But if you want to do this better, maybe you should just use different points. Maybe you can use these points. And suddenly, you see, for example, if you were to use these 2 points, that would be a very bad approximation. But by closing in to this point, you see you can get approximations to the first derivative in this other point. Now, what possibilities do you have to calculate these points? Actually, sorry, one too many. Let me just delete this blue point. Bad idea. Okay, I can't delete this one. Too tricky, but you can actually do the following. First of all, you can use this point, and you can use this point, and let's say this point. Then, and oh, that's very bad. And you can combine these two. That would be a no. But you can also use, let me just say, simply these 2 points and combine these two. Or you can actually use this point and combine these 2 points. Now, these all are called finite differences. And finite differences are used to approximate the derivatives. And depending on whether you use the midpoint or the right point and the left point and so on, you get different types of finite differences. We'll see these. And the result is that actually you approximate all those partial derivatives using finite differences. Say this in German again, so you get hopefully an even better understanding of what is going on here. Sie haben hier eine Differentialgleichung. Und Differentialgleichungen sind, wie der Name schon andeutet, schwierig und anspruchsvoll mathematisch, weil sie Ableitungen enthalten. Und jetzt überlegen Sie sich einfach nur mal kurz, wie haben Sie denn vielleicht sogar schon im Gymnasium, im Abitur, wie haben Sie Ableitungen angenähert? Ganz einfach über das Steigerungsdreieck. Ja? Wenn wir jetzt hier irgendwo einen Punkt haben und Sie bestimmen die Tangente an die Funktion, haben Sie ja schon die Ableitung. Wenn Sie jetzt die Tangente nicht bestimmen können, aus welchen Gründen auch immer, und Sie einfach links und rechts 2 Punkte auswählen, Sie wählen links und rechts 2 Punkte aus, legen einfach eine Gerade durch die beiden Punkte, so wie ich das gerade hier gemacht habe, zum Beispiel hier und hier, und Sie verbinden die beiden Punkte miteinander, dann ist klar, das ist natürlich jetzt nicht die Steigung der Tangente, die wir eigentlich haben wollen, aber Sie müssten ja nur mit dem linken und dem blauen Punkt einfach immer weiter nach unten gehen und Sie würden dann über letztlich hier ein anderes Steigungsdreieck, nämlich aus den beiden blauen Punkten, würden Sie jetzt hier plötzlich, würden Sie aus den beiden blauen Punkten dann und das Steigungsdreieck, würden Sie plötzlich eine Ableitung oder eine Annäherung an die Ableitung bekommen, die Sie eigentlich haben wollen. Was passiert denn da letztlich? Sie gehen im Grunde genommen vom Differentialquotienten zum Differenzenquotienten. Ja, Sie nehmen Differenzen. Sie nehmen ja letztlich die Abstände zwischen den beiden Punkten und dann nehmen Sie Differenzen und dieser Differenzenquotient, damit ersetzen oder mit dem ersetzen Sie den Differentialquotienten durch die Ableitung. Nichts anderes ist das. Also finite Differenzen, finite differences, ist natürlich erstmal im ersten Moment sehr, sehr ungewohnt und man denkt, das ist ja richtig was Anspruchsvolles, aber es sagt eigentlich nichts anderes, als dass Sie hierher gehen und mit dem Holzhammer die Ableitung, die partiellen Ableitungen einfach ersetzen durch Steigungsdreiecke. Ja, und dann sind Sie fertig und dann können Sie die Differentialgleichung natürlich relativ einfach lösen. Okay. So, as I just said in German, this is a very convenient way of solving a partial differential equation in a very nice way. And for the solution of this, we need to span a discrete lattice with dimensions, time, and underlying prices. So let T be the maturity of the option and S max a sufficiently large underlying price that cannot be reached. We need to set a maximum stock price because this is done in finite dimensions. The stock price, yes, in theory it can go up to infinity, but in practice it will never go as high as, let's say, 3 times the current stock price. Yeah. So the discrete lattice that we'll be using is S, the stock price, 0, it starts at 0, delta S, 2 delta S, 3 delta S, and so on. And then it's in time 0, delta T, 2 delta T, and so on until maturity. And we denote the individual values as follows. Fij is F at point I times delta S and J times delta T. So what are we doing? Let me use some, okay, I hope this is. So we start out here. Didn't I have point? Yeah, here, I have a point. Okay, point. So this is 1, actually this is 0. 1, 2, 3, 4, 5, 6, 7, 8 points in time. And then we have 0, 1, 2, 3, 4, 5, 6, 7, 8 potential stock prices. And then obviously for every combination of stock price and point in time, we have a point and this gives us a lattice. Ja, Sie sehen also, ich unterteile jetzt die Zeit und den Aktienpreis in den Underlying Preis in diskrete Schritte und ich bekomme so ein diskretes Gitter. Bedeutet aber dann auch, dass ich für jeden dieser Punkte, ich zeichne das jetzt mal einfach so, das geht also so, geht das Gitter natürlich weiter, lalalala. Und das bedeutet auch, das ist jetzt hier T, this is T0 and this is maturity, capital T, and this is a stock price of 0 and this is S max. Now, I want to compute all the potential option prices in this lattice. So maybe let's talk about which stock price, which option prices do we know? Well, obviously we know this column because at maturity the option prices Fij, Fi capital T, they are known because this is the option at maturity. And it's quite clear that this is obviously given by the payout profile, the payout function. Now for S max, we probably also know this. If the stock price takes its maximum value, then we can simply set S to S max and calculate the option payouts. Actually, we know this as well. If the stock price is 0, then we can immediately calculate the option price. And from these 3 columns, we can then try to calculate this, and so on. And we work ourselves through this lattice, through this grid, and then we get all Fij's. The question is, how do we get these? Quite simply, next slide, we are substituting the partial derivatives with the following different types of finite differences. For example, we can use the forward difference. That is, this point, if we are interested in the tangent in this point, we take this point and one to the right, and we approximate using the combination of these two. If we take the point itself and the previous one, we have the backward difference. And if we take one to the left and one to the right, and we combine these two, we get a central or a symmetric difference. Remember, this is what I've shown you here one, if you take this point and one to the right, forward difference. If we take this and one to the left, backward difference. And if we take one to the left and one to the right and combine these two, we have a central difference, quite simply. And then we substitute the forward difference by fi plus 1j minus fij divided by delta s. And the same for t, backward difference and central symmetric accordingly. That's all. Simply substitute the partial derivative in this function here by finite differences. Ja, einfach die partiellen Ableitungen durch finite Differenzen, also letztlich durch Steigungsdreiecke von zwei beliebigen Funktionswerten nehmen. And how do we choose these points? Fij, well, because we're using, sorry, oh, I jumped ahead again. Sorry, just jump back. Sorry, take a moment. We now use this lattice and we say, okay, if for example we are looking for this point here, then we take this point and this point, or we take this point and this point, remembering whether we are going through S or T, and then we can use these forward or backward or symmetric differences to substitute for these partial derivatives. The second partial derivative is approximated by, for example, using the forward difference, using this, so fi plus 1j, fij, fij, fi minus 1j, so again it's a forward difference, and then we need to transfer the boundary conditions. I've already done this. Actually here I've told you that these are the boundary conditions. Again, this is the payout profile at maturity, and for the maximum and the minimum stock price, it's very simple. Yeah? You can see here for the plain vanilla European put, we have in column N, that's the payout profile. For the minimum stock price, it's simply the strike discounted, and for the maximum stock price, it's always 0. Because for the maximum stock price, we cannot accept any payout. The option will always expire. We'll always let it expire. For the European plain vanilla call, it's exactly the other way around. In the last column, we again have the payout profile at maturity. In the first line, we have 0. In the upmost line for the maximum stock price, we have the maximum payout, which still needs to be discounted. Okay, so let's first implement the solution for the above PDE and a European plain vanilla put. And we approximate the partial derivatives to S using symmetric differences and the derivatives to S using backward differences. You can combine this. You can use different finite differences for S and for T. So as a result, we get this equation, Fij minus Fij minus 1 divided by delta t plus plus plus. This is simply the Black-Scholes partial differential equation with the partial derivatives being substituted for by the finite differences. Then let j equal to n, we go back in time, and together with the nth boundary condition, this value fin minus 1 is an unknown function depending upon 3 known values. So if you solve this, you have to rearrange this. We have to rewrite this and get what we call an explicit scheme. Fij minus 1 equals, and so on and so on. This is not very, doesn't look nice, let's be honest, but everything is known. So everything is known here. Delta t is known, sigma is known, I is known, R is known, and so on. You have to calculate A star, B star, and C star. Insert this, and as you can see, Fij minus 1 is a function in Fi minus 1 j, Fi j, and Fi plus 1 j. So if you know j, you can calculate j minus 1. Then you go back in time, one more period, and again, and again, and again. This looks pretty much like what we've done before with the binomial and trinomial model. It's quite similar to that because, again, we're using a discrete lattice. So let's implement this in MATLAB. We call this European put explicit scheme. and we need our actually the same input parameters as before, but we need a maximum stock price. And then we have to set up our grid, adjust the increments if necessary. We divide Smax by ds. We need to round this. This is supposedly a discrete letters. ds is Xmax divided by m. N equals round t divided by dt. And then dt, the steps in time, is t divided by n. And then we set up the lattice, which is done by linspace, linear space in MATLAB. And then wet I, wet j, those are our indices, and set up the boundary conditions. Last column, first line, last line for the European put. We set up the coefficients a, b, and c, and then we solve it backward in time. That's the function we've just seen. ai times matval plus bi times the value in the linear space plus ci times this value, and return the price. But it might be that actually let's assume we go back here. Now let's assume we've solved this, and we are interested in one column actually, which is this one here, because this column gives us the option prices for all the potential current stock prices. Now what could happen is that actually the current stock price is here. It's between this point and this point. So we know the option price here and here. And what we are doing now is we simply interpolate between these two. For example, this is the first price and this is the second price. And we interpolate and we say, well, the stock price is currently here. Then the option price is assumed to be this point. That's the explanation for the last line in this program here. Price equals interpolate that as matval for S0, the current stock price given to us as an input parameter. That's S0. Okay, so let's do this and compare our results with the Black-Scholes price. Have a look at these functions for a minute and see what happens. You can see the Black-Scholes price is 4.076, and if we use the explicit scheme with the finite differences, we get a price of 4.0669, so quite close to the Black-Scholes price. Slightly different parameters. Black-Scholes price now with this slightly different model. This is actually, if we see this correctly, this is a slightly different volatility. We get 2.8446, and with finite differences 2.8288. So again, we get quite close to the Black-Scholes price. Now let's use something different. Actually, we are using slightly different parameters here. Everything's the same except that, let me just see, we use not, I think this is 100, and let me just see, this is actually the different steps in the stock price. It's ds, and actually here we used ds as a difference of 1.5. Here we're using 1. What happens now is that suddenly finite differences explodes in value. It's a huge number, so something is going wrong. Now, in this last calculation, we can see that the approximation with finite differences can be numerically unstable in some cases. And one way to avoid these problems is to use a so-called implicit scheme. So for this, we use forward differences, and we obtain this slightly different lattice. Again, you can see this is the derivative of f with respect to t, and this is with respect to s, and so on. This is r times f, and the lattice is then written by AI times plus BI plus CI and so on. And in this case, we have 3 unknowns and only 1 known variable. And the other 2 unknown values are clearly defined by the boundary conditions. Again, we have to go back in time, get the solution of the following linear system of equations. We need to solve this. And then this coefficient matrix is tridiagonal, constant, and also sparse for each time level, so that the solution of the SLE can be accelerated by the LR decomposition method we've already seen. And below, let's do this again in MATLAB using finite differences, but now with an implicit scheme. Actually, it needs to be, have a different name. It's also called explicit. This is the implicit scheme. So we again set up the grid, adjust the increments if necessary, set up the linear space, set up the boundary conditions. We set up the tridiagonal coefficients matrix A, B, and C, put it into this, the coefficient matrix using these diagonals. And then we have to solve the system of linear equations using the LR decomposition. And then, after having done this, well, we again need to interpolate the payouts and the prices. And we do this using the VAT-S matrix and MAT-VAL matrix using the current stock price as 0 as the point at which we are interpolating these option prices. Okay, so this is option pricing using finite differences. The finite differences, again, are used to substitute the partial derivatives in the Black-Scholes option pricing partial differential equation. And you can apply Monte Carlo simulation and finite differences every time you don't have an analytical solution to the Black-Scholes model. If it's a plain vanilla derivative, you don't need all these methods. It will only take up computational time. But if you have an exotic option, you can use Monte Carlo simulation and finite differences. Okay. So next, in our penultimate chapter here, we want to look at interpolation. Completely different topic. You can read about this in the Brandi-Mate textbook. And every now and then you need to approximate functions and you need to interpolate. Now, the approximation of a function is often needed in many applications, in mathematics, in engineering, but also in finance. A very simple example we've already seen is the evaluation of a standard normal distribution function using this integral. And on the next slide, you will see how actually you can calculate an integral using function approximation. So what can be done is you can use quadrature, but the approximation of the integrand and the exact integration of the simpler approximation may be recommended. So it might be easier to substitute the function by a simpler function and then integrate exactly. Under certain circumstances, the function of interest is also only known on a discrete grid, and consequently a continuous approximation is needed running through the given discrete points. Also, in some cases, we only need a local approximation. A local approximation will suffice. And then you have a given point x0, a potentially small surrounding environment of x0, and then you need to locally approximate f. Very famous example is the Taylor series. You might know, I mentioned this, Taylor's theorem states that you can approximate and substitute a function in the vicinity of a point x0, might be very small, by substituting it with its Taylor series. The Taylor series is given by f of x0 plus first derivative at x0 times x minus x0 and so on. This is the Taylor polynomial, Taylor series. And you can see on the right hand side you have polynomials. So actually, regardless of what f looks like on the left hand side, it's substituted with a Taylor polynomial series. and we can have a look at this in a more general way. So let Pm of x and alpha be a polynomial of degree m with coefficient vector alpha. Could be, for example, P0, P1, P2, P3, and so on. Well, polynomials are known to be infinitely differentiable, so that they are well suited for both integration and differentiation. Very, very simple functions. And we want to use these simple functions in the next step to substitute and approximate more complex functions. Ich sage das jetzt mal kurz auf Deutsch. Polynome werden jetzt hier benutzt, um andere Funktionen zu ersetzen, weil Polynome sind beliebig oft integrierbar und differenzierbar. Ich kann eine beliebige Funktion f durch die Polynome ersetzen. Und die Frage stellt sich dann natürlich einfach, ob diese Approximation gut ist und ob dementsprechend auch hier ich dann einfach mit den Polynomen weiterarbeiten kann. Now, if we use a polynomial for the approximation of a given function, we need some kind of metric to evaluate the quality of the approximation. And suppose now we have n values for a function f at x1, x2, x3, and so on. We want to approximate, and then the quality of the approximation using a polynomial can be judged using the metric, and this is one potential metric which we'll use. Take those function values that are known f of xi minus the corresponding value of a polynomial at this point, take the squared value, sum them all up, and use and minimize this squared error sum over the coefficient vector alpha. By minimizing this metric, we can now search for a suitable polynomial Pm. And obviously, other metrics could be used as well, but here we use the squared sum of errors. Now, another approach is to use linear combinations of basic functions to approximate a function. Now, actually, this could be also done by polynomials. If you assume that the phi j function, these basic functions, that these are monomials, x squared, x taken to the power of 3, to the power of 4, and so on, those are monomials. It's actually the same way. We would again get a polynomial of degree m, but we want to use this in a more general way, so we use basis functions that span a linear space, and then we use basis functions and linear combinations of these basis functions to approximate f. And the approximation task now is to determine the corresponding coefficients of the function on the right hand side, and to choose the coefficients cj in such an optimal way that, for example, this metric becomes minimal. That's our task. Now, if the function's approximation is done using least squares, we use, for example, n nodes, Stützstellen in German, where the value of the function f is known. For n being larger than m, we have too few degrees of freedom when trying to reach an exact approximation with a linear combination. And then the approximation takes place via solving the system of linear equations that is given by this here. We have to choose the coefficients cj in such a way that at least at these points xi, the approximation on the left-hand side is equal to the function that needs to be approximated. Wenn Sie also hier eine solche Approximation vornehmen wollen und Sie haben mehr Stützstellen als m, als Koeffizienten, dann ist klar, dass es ein lineares Gleichungssystem ist. Auf der rechten Seite haben Sie die Funktionswerte, die Sie approximieren möchten. Und auf der linken Seite ist die Funktion, mit der Sie approximieren, nämlich hier die Linearkombination Ihrer Basisfunktionen. Und das muss dann übereinstimmen. Ja, in Matrix Notation, this is phi times c equals y. Y, those are the function values, and f of x, I. And phi of ij, those are the values of the nodes at the basis functions. Now, for n being larger than m, the system of linear equations is not solvable. Consequently, we need to find an approximate solution, and then we are led to the method of least squares. Ja? Das ist hier klassisch. die Methode der kleinsten Quadrate, die Ihnen hier wieder begegnet. So for this purpose, we are looking at the sum of the squared residuals, of the squared errors, EI, that is the function value at xi minus the value of the approximating function. And it's well known from statistics, for example, that the least square solution is given by phi transpose times phi inverted times transpose of phi times y. If we have n nodes and m basis functions, actually we get the following relation. This applies exactly. Ja, wenn Sie n gleich m haben, wenn Sie also für jeden Punkt, den Sie approximieren wollen, xi, eine Basisfunktion verwenden, then the result is exact and we call this interpolation. Ja, dann interpolieren Sie. And let's show you this in MATLAB. The x data is 1, 5, 10, 30, 50. The y data is the logarithm of x data. So actually the function we want to approximate is the natural logarithm. So we plot this using little circles. So these are the 1, 2, 3, 4, 5 points. Now, what would, for example, a function look like if we were to approximate these 5 points using only, let me just think, 2 basis functions? Think about this. How would this look like if we were to use 2 basis functions? Quite simply, you can think about this in the following way. What would you do if you only have 1 basis function? Well, would be 1 point. Not a pretty good approximation. If we have 2, well, we get a line, or maybe probably rather such a line. We'll start out here, and this will be the approximation. If we have 3 points, if we have 3 basis functions, it will probably look something like this. And if we interpolate, it will look like this. Hopefully, we'll go through all those points. Problem is that if it's an interpolating function, it might look like this. We'll go through here, these points, and then go through this point again. Not very exact. It will fluctuate and then go through here. That's what will happen. First approximation is using a second degree polynomial, a times x squared plus bx plus c. So we use the monomial basis. This corresponds to the choice phi 1 is 1, phi 2 is x, phi 3 is x squared. And we use the MATLAB function polyfit to arrive at the least squares method result here. So polyfit gives us these 3 coefficients. We plot this, and this is the result. So as you can see, this is an approximation. It's not interpolation. We are only getting closer to a function that runs through these points. Again, the true function is the logarithm, which will look like this. Yeah? That's the logarithm we are looking for. Now, an increase in the polynomial degree allows a more accurate approximation. So we are now using 4 monomials. And what we get is actually interpolation. But as you can see here, this function, this polynomial, starts to fluctuate. It doesn't continue like this, like the logarithm does, but it fluctuates in between. This is a problem we'll later see with polynomials. Polynomials fluctuate, yeah? Or rather oscillate. Ja? Polynome, wenn man sie für die Interpolation nutzt, oszillieren, bedeutet, sie schwanken ganz extrem zwischen den Schnittstellen. Wir werden später sehen, wie man dieses Problem umgehen kann, aber hier, gerade mal beim Polynom 4. Grades, erkennt man schon, wie das langsam anfängt. So at this point, let me briefly explain interpolation using polynomials. We are given a set of xi, yi's at points of a function f that is to be interpolated. So xi are the nodes and yi are the functions at which the function is evaluated. Now, instead of the monomials, we are using the Lagrange basis polynomials. If you remember your math lectures in the first and second semester, polynomials form a linear space. Polynomials form a vector space, and for every vector space we have unlimited different sets of bases. Ja? Polynome bilden einen Vektorraum. Jeder Vektorraum hat unendlich viele Basen, also eine Menge an Basisvektoren, die den linearen Raum aufspannen, sodass sie jeden Vektor als Linearkombination dieser Basis darstellen können. Und wenn Polynome, doch endliche Polynome erstmal, einen Vektorraum darstellen, was sind denn dann mögliche Basen? Die Monombasis haben wir hier gesehen. Das ist die Monombasis 1x, x², x hoch 3, x hoch 4, x hoch 5. Damit können Sie als Linearkombination jedes Polynom darstellen. A different basis are the Lagrange basis polynomials. So they form a basis of the vector space of polynomials. And we say the interpolation polynomial is unique, and it's given by actually the sum from 0 to n of yi times li. Although Pn is unique, it can and should of course also be displayed and represented using other bases. Meaning what in German? Wir schauen uns hier das sogenannte Interpolationspolynom an. Das Interpolations- oder das interpolierende Polynom ist eindeutig. Es ist eindeutig in dem Sinne, dass wenn Sie eine Basis festhalten, in dem Falle hier die Lagrange-Basispolynome L1, L2, L3 und so weiter, dann ist das Interpolationspolynom eindeutig und das Besondere, deswegen nimmt man die hier, die Koeffizienten sind gegeben durch die yi-Werte der Stützstellen. Dann ist Pn eindeutig. Sie können es natürlich auch hinsichtlich anderer Basen darstellen, wir müssen einen Basiswechsel durchführen, aber das Interpolationspolynom ist eindeutig. Let's look at an example. We now use 10 points, x1, 2, 3, 4, 5. Those are the y points. And we plot those with circles again. We use polyfit and plot polyfit. As you can see here, we now have 10 different points, and especially at the boundaries, it oscillates extremely, goes up and down close to infinity. So this is the interpolating polynomial. If you use more nodes, it will be a polynomial of higher degree and it will oscillate even more. If you only have 2 points, well, then it's clear it's simply a line, it will not oscillate. If you have 3 points, it will probably look like this. If you have 4 points, it will probably look like this, and so on. You get the idea. Using a polynomial of higher degree will lead to more oscillation. So this suffers from oscillation. This problem cannot, however, be solved completely. You can use a different set of supporting points of different nodes. You can use a different basis. For example, we can use equidistant points. That was our standard here. Those were equidistante Stützstellen. Or we can use the Chebyshev supporting points, which are given here. They are slightly different. If we are able to set those supporting points, those nodes, we can do so. Then we should, for example, use the Chebyshev supporting points. And let's use this to interpolate the Runge function, 1 divided by 1 plus 25 times x squared. And if we use the Chebyshev nodes instead of equidistant nodes, you can see that this is using the equidistant point. It oscillates from -1 to almost 6. And if we use the Chebyshev supporting points, it will oscillate from less than 0.5 up until 1. So we have, again, we are running from -5 to 5. So there's less, even though this looks worse, actually the scale is different. So actually here the Chebyshev supporting nodes, they will reduce oscillation, but they still oscillate. Yeah? So this is a huge problem actually with polynomial interpolation. and this can be solved by using spline interpolation. What is spline? What are splines? Actually, spline, the idea of splines are, we've seen that actually polynomials are a good choice, but polynomials are only a good choice as long as you use polynomials of lower degrees. So what we could do, for example, is we can start out by simply using linear polynomials. Let's say something that looks like this. Again, this would be an approximating function, not an interpolating function, but this would be a set of linear functions being glued together. Quite interesting idea. Problem is that, as you can see, here and here, at those points at which the polynomials, the linear polynomials, are glued together, the function is neither differentiable once or twice, it's only continuous. So what you're doing is, actually we could have also done something like this. We could have done something like this. Then of course, at some points the function is not even continuous. But we want, this is quite clear, this is where the function is not continuous. So we want to use polynomials of lower degrees. We want to glue them together, but we want the functions to be differentiable. We want them to be as smooth as possible at those gluing points. Was wir also machen hier, ich sage das nochmal auf Deutsch, was wir hier letztlich machen ist, wir haben ja gesehen, dass die Polynome, die keinen so hohen Grad haben, dass die relativ gut sich eigentlich eignen für das Approximieren. Die sind eben nicht so genau, aber sie oszillieren nicht so stark. Was ich also machen könnte, als erste einfache Idee, ist ja zu sagen, ich nehme einfach lineare Polynome, also lineare Funktionen sind ja ganz einfache Polynome, und ich stückel die so zusammen, dass sie möglichst gut die Funktion approximieren. Es könnte dann zum Beispiel so aussehen. Das ist ja schon mal eine gute Approximation. Problem ist natürlich, dass das, was ich dann hier rausbekomme, wenn ich die so stückweise linear definiere, dass die Funktion, die dann resultiert, an diesen Nahtstellen nicht stetig, nicht differenzierbar ist. Sie sind zwar stetig, ich habe keine Sprungstelle, aber es sind immer noch Funktionen hier, die in diesem Punkt und hier nicht differenzierbar sind. Und das mache ich bei den Splines. Ich verlange, dass diese Polynome so zueinander gestückelt werden, dass sie dann an den Nahtstellen stetig und einmal, vielleicht sogar zweimal oder noch mehrmals stetig differenzierbar sind. Und das, was dann resultiert, nennt man einen polynomialen Spline. Und das sieht dann möglicherweise so aus. Okay, jetzt habe ich hier eine Knickstelle drin, das ist natürlich, das müssen wir ein bisschen glatter machen. Dann könnte das so aussehen und ich bekomme plötzlich eine Spline-Funktion. We will be using polynomial splines, and actually I want to show you this here. This is a result, actually. Remember that we used the Runge function with equispaced, equidistant points and the Chebyshev nodes. And actually, as you can see here, using spline interpolation reduces the problem of oscillation, especially in this point, last example here, almost completely. We can see that on the right-hand side here, we only need a linear function for this part and a linear function for this part, and we are done. And in between, we need a slightly different polynomial. And by gluing polynomial pieces together, requiring that at the nodes, it's continuously differentiable and sufficiently smooth, we get a polynomial spline, which can then be used for function approximation. Splines are the weapon of choice when it comes to function approximation in many of our applications, and it will later be used to approximate term structures of interest rates. Splines nutzt man insbesondere bei Zentralbanken, um natürlich jetzt nicht nur Funktionen zu approximieren, sondern ganz konkret, um die Fristigkeitsstruktur der Zinssätze approximieren zu können. And I think we are quite well on time in this semester, so we only have almost 50 slides left. So I would say we can stop today here. Please have a look at spline interpolation, how it works. If you understand the general principle, meaning that you are taking polynomials and you're gluing together polynomial pieces, and then you get polynomial splines, and these are continuously differentiable, and then these functions are used to approximate and even interpolate different functions. Okay, so if you have any questions, please stay in the Zoom room. Otherwise, have a nice week. Thank you.